Okay, a video for Monday, March 30th. Today's topic is going to be specific heat. By the end of the lesson, you'll be able to learn, you'll be able to determine why different materials will heat up at different rates. Now, what we're going to use for that is specific heat. Specifically, we have to talk about specific heat. So now, specific heat, here's the unit. Joules per gram degree C. Remember, dividing line means per. Joules per gram degree C. Now, if we wanted to summarize joules, joules is a unit of energy, and only a unit of energy. So we could look at this unit and say, okay, specific heat is the amount of energy needed to raise something's temperature. Here's degree C, right? So the amount of energy needed to raise something's temperature by a degree C. And we have the gram in here because if we want to compare different materials, they have to weigh the same, right? So specific heat definition is joules per gram degree C, or the amount of energy required to raise 1 gram of a material by 1 degree Celsius, right? So for specific heat then, if you have a high specific heat, if any object has a high specific heat, what does that mean? High means a lot. High means I need a large amount of energy, to raise the temperature of 1 gram by 1 degree C. So high specific heat means I need a lot of energy. So the way you could think about this is that high specific heat equals hard to heat up. How are you going to remember that a high specific heat is hard to heat up? Now, one of the materials on Earth that has very high specific heat is water. Okay? Water, the specific heat of water is 4.184. What does that mean? It takes 4.184 joules of energy to raise a gram of water, which is a milliliter, by 1 degree C. Now, if we want to compare that to, say, aluminum, right? Aluminum specific heat is about 0.9, okay? So it takes 0.9 joules for each gram of aluminum to raise by 1 degree C. So if you notice, it takes about 4 times as much energy to heat up a bucket of water as it does to heat up the same amount of aluminum, the same mass. Now, don't get confused with what it takes to melt, right? Aluminum melting point is much, much higher than water, right? Water melts at 0 degrees Celsius, 32 Fahrenheit. Aluminum melts at who knows what, thousands of degrees, right? But it's still easier to heat up the aluminum, right? Now, if we looked at, say, wood has a higher specific heat than aluminum or steel. So if wood has a high specific heat means hard to heat up. So very often, say you have a fireplace poker, right? And you're going to poke the logs in your fireplace. It's made of steel, and the very end handle is wood. Wood is harder to heat up. It doesn't conduct heat as well. And so you put the handle made of wood, so the steel can be very hot, right? The steel poker can be hot for your fireplace, but it won't burn your hand. Because water has such a high specific heat, water has a moderating effect, right? It takes a lot of energy to heat it up and a lot of time to cool it back down. Okay, so let's take the summer in New England. The water temperature in Old Saybrook is very cold in the spring. It gets warmer and warmer and warmer because water heats up slowly. It's hard to heat up. So the nicest swimming water temperature ends up being around, say, September 1st, right? But then what happens? Then the days get cold, and you can have a very cool day on the beach, but the water stays warm into October, November, or warmish, because the water heats up slowly, and therefore it cools down slowly because it has a high specific heat. So the moderating effect of the water and how it absorbs and releases energy is how some cities on the coast remain very nice temperature even though it's hot. I once made a drive in the summer from LA straight east to Bakersfield, California. So that's LA to Bakersfield, California. And in LA it was a hot day and all, but there was a breeze and the air temperature was 90-ish. But it was okay. So I get in my car. This is an old junky car with no air conditioning. Oh my. By the time I got to Bakersfield through the desert, it was 117 degrees Fahrenheit. I don't know what that is Celsius, 35. And 117 degrees Fahrenheit is so much that air conditioning, forget it. It's impossible. It doesn't keep up. Now, if you notice, LA and Bakersfield, they're in the same latitude, right? The same distance from the equator. The intensity of the sun is the same. But because LA is on the coast, all this water here is absorbing a lot of that energy, right? Bakersfield is in the Central Valley, surrounded by basically dry earth, which heats up very quickly, right? So earth itself, high, has a low specific heat and water has a high. So the same intensity of the sun in Bakersfield to make it baking hot in LA is cooler because the ocean water is absorbing it. A practice problem with you right now, and one thing I want to point out here, right? So in the practice problems, here's the note sheet. Notice it says specific heat, joules per kilogram degree C. Again with the units. So we got to be aware of that. So if we want to go back to our normal specific heat unit of joules per gram degree C, we're just going to move a decimal 3 places. So let's look at the first practice problem, right? First practice problem says how much heat energy is required to heat 0.35 kilograms of gold by 40 degrees C. Okay? 0.35 kilograms. Okay? So what do we know about this? We know we want to have our formula, Q equals MC delta T. They asked us for how much heat energy, right? So we're looking for this one, right? Do we know mass? We do. It says 0.35 kilogram. Let's convert it to gram. Kilo is 1,000. So I have to move the decimal from kilo to gram 3 places. So that, when I go 1, 2, 3, that is 350 grams. Okay? So we know that for the mass. Now, the material was gold. Okay? So do we know the specific heat of gold? On this specific heat note sheet, we're going to go up and it says here gold is at 129. Now, it's 129, but that is kilogram. So I got to move it over again. Okay? So if the specific heat here is 129 per kilogram degrees C, I need to go 1, 2, 3. So the actual specific heat, we're going to go like this, move it over 0.129, and that's going to be joule per gram degrees C. Good? Now, temperature final minus temperature initial. Do we know that? It says if you're going to heat the gold up by 40 degrees. If you heat something by 40 degrees, increase it by 40, that's the change. We don't know the start or the end. We just know the change. So I don't, in this case, don't need temperature final initial. I know that I'm going to heat it up 40 degrees C. Okay? So now that I have mass here, and I moved it to 350 grams, I have specific heat of gold, 0.129, and I have the change in temperature is 40. Okay? So now when I just do this math, this times this times this gives me a number. Will I get the unit of joule? Let's look. Here's gram on top and gram on bottom. That's going to go. Degrees C on top, degrees C on bottom. That'll go. I'm left with joule. So this times this times this is the answer. Type it in and away.